In our last discussion, I introduced the concept of the normal distribution to you, and specifically we ended with a brief discussion about the standard normal distribution. You see a picture here with the standard normal curve. The table that we're going to look at is a cumulative table. Now, what we know about the standard normal distribution is it's centered at 0. It has a standard deviation of 1, which is kind of hard to draw a picture of, honestly, but the standard deviation, as we've seen throughout the semester, gives us an idea how far observations fall away from the mean. We expect in normal distributions, let's see, what do we call them earlier? Mound-shaped symmetric distributions according to the empirical rule. We expect most of the data, about 95%, to fall within 2 standard deviations of the mean. So in this picture, between plus and minus 2, right, a standard deviation is 1. When you go 2 standard deviations around the mean, you get to plus or minus 2, and we expect approximately all, according to the empirical rule, to fall within 3 standard deviations, or within the values plus or minus 3. So when I get out here, pretty far out here in the tails, we're talking about plus or minus 3, and then you get plus or minus 2, plus or minus 1. You can kind of break the distribution up. Well, the empirical rule just kind of lived on those 1, 2, 3 standard deviation lines. The normal distribution is going to be more accurate. It's going to be better than that. And the key thing is, we're working with a cumulative table. We're working with a less than or equal to type of probability. Sometimes we just say less than, sometimes we say less than or equal to. With a normal distribution, with a continuous distribution even, we know the probability of the equal to is 0. So I don't care if you write it as less than or equal to or as less than. Doesn't make a difference. So in this lecture, in this discussion, what I want to do with you is go through and introduce how we use our cumulative table. And I should mention there are several tables. There's at least 3 different normal tables that exist. And here's what I typically tell students. When you're good at working with normal distributions, when you're really good at working with the table that you're working with, you can use any of them. It's really easy to transition from one to the next to the next. However, when you're first starting out, which is probably many of you, if not all of you, probably learning the one table that I go through with you guys here is your best strategy. And the table that we're using actually works really well with the software we're using as well. And so I'm going to gear these discussions towards the cumulative table, and then transitioning and hopefully eventually getting to where we can use Excel, because Excel has some fabulous functions that we're going to use. And you don't hear me say that all the time about Excel. I have a love-hate relationship with Excel. I love it a lot. I hate it occasionally. But when you're working with normal distributions, it really does a good job. Better than anything else I've ever used. So let's go on. Let's move on. And let's start with an example. Let's start with a probability. And there's really 2 types of problems when you're working with normal tables or Z tables. One is a probability type problem like this, and I'm asking what's the probability Z, the standard normal random variable Z, is less than or equal to the value 1. And before I bring the table in, I just want, there we go, that's what I want. I want a picture of the standard normal distribution, and I'm going to put a value 0. I'm going to label this thing as a Z. Occasionally I'll put that little doodad in there because my Z's look like 2's occasionally. And now I got to locate the value 1, 1.00. Well, it's a positive number. It's 1 standard deviation above the mean. Now, I'm going to draw it over here, and my stinking pen is going nuts. I don't know why it does that. It's probably my mouse. But I'm going to shade, and I'm going to take advantage of all those lines. I'm going to shade less than the value 1. And so everything over here to the left is what I want shaded. This is going to be a fun lecture video, folks. That's what I want. And fortunately, that's the kind of probability I get from my table, my standard normal table, my cumulative table. And when you find this cumulative table, you're going to see a couple of them as I go through the examples here. There are really 2 pages to the cumulative table. There's the page that you're looking at here, which has z-scores that are positive numbers. And the way that we read this table, you go to the first column and you get the first decimal place of the z-score. This table gives me z-scores to 2 decimal places. I want to look up the z-score 1.00, so I come down here and I find the 1, and then I get the second decimal place up here. So I match those 2 up. If I wanted to find the z-score 1.23, I would come down here and get the 1.2 here, and I'd come over to the 0.03 column, and I would match those 2 things up. And the place where you match them up is the cumulative probability, that red shaded region, even though it looks really jagged. I'm going to be a little salty about that. Even though the cumulative probability less than or equal to 1, is the probability 0.8413. That's what the table tells me. If this value was 1.23, if I said find the probability z is less than or equal to 1.23, I would come over here in the table and I'd match up the 1.2, the 0.03, and that would be the z-score 1.23, and you see the probability here is 0.8907. That's how this table works. That's also, by the way, and I'm going to try to use my keyboard now to do my animations because I'll be a little bit finer. That's also how the normal distribution function, the norm.dist function in Excel works. You put the value you're interested in first. That's the value of x. That's the 1.00. That's the number I asked you about. You put in the value of mu second. You put in the value of sigma third. I'll put commas between these. And then you have the option of true or false. For the cumulative probabilities, we always use true. And so if I went to Excel, opened up a spreadsheet, and typed equal norm dist, open parenthesis 1, 1, 0, true, close that parenthesis and hit equal, it would tell me, and actually it would tell me this probability to like 50 decimal places. It's crazy with its accuracy. But if I reduced it to 4 decimal places, it'd give you 0.8413. And so you can think of the normal distribution function, the norm.dist function in Excel, as a software option for this table. They're interchangeable. You get exactly the same information. And as you're going to see, especially here in this next problem, that the information you get from the table, from the norm.dist function, isn't always the answer you want. Look at this problem. I want to find the probability that the standard normal random variable, and again, I can put 0 here in the middle. I'll label this is my distribution of z's with my crazy mouse thing going crazy. The value 0.32 is again above the mean. It's not quite as far out, but this time I want the greater than probability, so I'm going to shade here to the right. That's not the probability I get from my table, right? The table is going to give me, and I'll try doing polka dots and maybe my mouse won't freak out as much. I want the right hand, the upper tail probability, yet my table is going to give me, when I'm drawing these little red dots or polka dots, it's going to give me a less than or equal to probability. So when I look up the z-score 0.32, and I'm going to just come over here and grab it right here, I got the 0.3, I got the 0.02 up here, I match these guys up, there's the z-score 0.32. It tells me this probability on the left hand side is 0.6255. Well, that's not the probability I want. I want the probability to the right. So how do we figure that out? Well, we know a couple things about probability distributions. We know the area under the curve has to be 1, so I'm going to take 1 minus that 0.6255. The probability above the 0.32 is a 0.3745. Now, how would I get that in Excel? Well, I would get the less than or equal to probability. I would do the norm.dist. I would use a 0.32 as the value of x, or z, I guess better wording here, the value of z that I want to use, the z naught value, so to speak. The mu is 1, the sigma is 0, and true. I want you to get comfortable. In fact, I'm going to require you to get comfortable working with the norm.dist function. Okay, so a couple good examples of working with the normal distribution. Let's take a look at a couple more. The probability that the standard normal random variable is between a negative 1.5, so I'm going to draw that over here. Remember, we got 0 here, so this is going to be my negative 1.5, and a positive 0.61, which is going to be over here. For the most part, I'm going to say it doesn't matter if you draw this thing together. Now, you need the 0.61 on the positive side. You need it above 0, you need the negative 1.5 below the value of the mean. But as far as, oh, I got to really be careful about how far I put it to the right, nah, not so much. We want the probability in between. Look at me, living on the edge with these lines, kind of keeping my fingers crossed, hoping that I don't run into problems. So what do we use? We use our normal tables. Now you can see that I've kind of taken that first table that was on the last page, and I'm just giving you the top part. And the reason I'm giving you the top part of that, because I need the z-score 0.61. There it goes. Look at that stinker. 0.61. There's my 0.61, right? And so I see this probability. That's not the probability that I want. That's the probability, I'm actually doing that on purpose. That's the probability below 0.61. When I come down, there's the second page of the table has negative z-scores, and you can see I've done part of that. I need to get to the z-score negative 1.50. There's negative 1.5. I'm going to match that with the 0.00 column here. And I see this probability, 0.0668. That's this probability. Let's see if I can shade it. That's the probability over here, less than a negative 1.5. This should remind you of some binomial work that we did, right? We're going to take those two numbers and subtract them. 0.7291 is the probability below the 0.61. I don't want all that probability. I just want from 1.5, the negative 1.5 to the 0.61. So I subtract from it the probability below the negative 1.5. I can find the norm dist for the 0.61. That gives me the 0.7291 when I'm in Excel, and I'm going to subtract from it the 0.0668, which I'll get using the norm.dist function using a negative 1.5. Play around with it, see what you think. You can use them interchangeably. Now I'm going to say when you're working with standard normals, it doesn't matter which of these techniques you use. If you want to use a table, go for it. If you want to use the norm.dist function, that'll work too. However, I am going to give you a little heads up as we move into other normal distributions, non-standard normal distributions, which is where we're going next. The normal distribution function is going to be the best way to do it. It's going to be easier. You'll see that in some work I'm going to do in a little bit. Let's take a look at one more here. This time, what am I doing? I'm switching the signs. I'm making them both positive numbers. And yet the way that we're going to solve this is exactly the same, except now, this is supposed to be 1.5, sorry about that. I'm going to look up a positive 1.5, which you can see is right here. 1.50 gives me the z-score, or the z-score of 1.5 gives me a probability. So if I look at everything this direction, if I shade under the curve over there, that's 0.9332, and we already know about 0.7291, so I'm going to subtract them. And again, let's see what we look at in Excel. We're going to subtract to. We're going to use a normal.dist function twice. You get it for your biggest number first, and the biggest z-score here was 1.5, the smallest z-score is 0.61. In the last problem, the biggest z-score is 0.61, the smallest was negative 1.5, and you're subtracting them. You're going to find every time I ask you the probability between two values, I don't care if they're on either sides of the mean like they were in part C, if they're on the right-hand side like they were in part D, or if I draw you another picture. What if the probability was between negative 0.61 and a negative 1.5? You're going to get exactly the same probabilities you do in part D, because you have a symmetric curve around this value 0. Working with probabilities, you need to be able to work with normal probabilities. All right, so that's working with probability problems. The next step is to take a look at another type of problem. Find a point in the distribution z0 such that the probability z is less than or equal to z0 is 0.8438. The toughest thing about these problems is getting them set up. How do you figure out where the z0? Well, I know the probability. If I shade the region over here, when I look less than or equal to 0, what do you see? Well, we know that's 0.5. I want to see more than 0.5. When I look to the left, this less than or equal to here says look below. When I look below, I'm going to see 0.8434. There's no way I can have a value of z0 out here. There's no way I can find z0 and say, oh, look at the probability in the tail out here is 0.84. There's no way, because I know the probability below 0 is 0.5. So I need more than 0.5 below this point that I'm looking for. So that's going to tell me that z0 has to be up here. And that less than or equal to probability, that total shaded region that you see that now, the red, all of it that's below the z0, that's the 0.8438. So let's bring in the table. And again, I'm bringing in the positive z-scores because I'm above the mean. I'm looking for a, this is going to be working it different. The last problem is A through D. I gave you z-scores and asked you for probabilities around it. Here, I'm saying here's a cumulative probability, 0.8438. Go find that. Go find that in the table. Let's take a look in the table. See if you can find a probability. Ooh, what am I seeing right about here? And it's messing up big time. I'm seeing a probability of 0.8438. There it is. What's the z-score where that happens? Well, it's kind of tough to see. It's 1.0, and look at this column. It's in the 0.01 column. This is the z-score, 1.01. That's how you use a table. You have to think in terms of cumulative probabilities. Now, this was a less than or equal to probability I gave you. The next one's going to be a little different. So you got to think in terms of less than or equal to probabilities, and then you find it in the table. And when you find it in the table, you go to the row and the column and try to figure out the z-score. Now, in Excel, there's another normal function. It's not the norm.dist, it's the norm.inv. It's a normal inverse function. And the normal inverse function, you got to put in a less than or equal to probability. You put in a value of mu, you put in a value of sigma, and again, I'll put commas in between these things. And that's how you find, when you do equal norm.inv, open the parenthesis, put 0.8438, comma 1, comma 0, close that parenthesis and hit the equal sign or go or enter. It's going to give you a value of 1.01. And again, it's going to give you a value of 1.09994. It's going to give you it to like crazy decimal places. You can get the same exact information using the normal inverse function that you can using the cumulative probability table, the Z table. All right, let's take a look at another one of these. Find the point in the distribution such that the probability Z is greater than Z naught is 0.6628. So again, really what you have to do is come up with the less than or equal to probability. I mean, I'm going to draw the picture, but you need the less than or equal to probability. If there is 0.6628 above, doesn't that mean there has to be, let's see, I got to make these things sum to 1. Doesn't that mean there's 0.3372 below? If there's 0.3372 below and 0.6628, I hope you can see this value of Z's got to end up over here. The 0.3372 probability is what I've shaded here in red. Now let's bring the table in. And again, because I'm looking on the left-hand side, I brought the negative. See all the z-scores here? We're on the lower side. There's two sides to this table. There's two pages. There's the negative z-scores, and there's the positive z-scores. All the probabilities on the negative z-score, because they're cumulative probabilities, are all going to be less than 0.5 or go up to 0.5. You can see when the z-score is 0 down here at the bottom, the probability is 0.5. But I don't want 0.5. I want 0.3372. Where's that at? 0.3372. Where the heck is it? I can't seem to find it. 0.33. Here it is. What's the z-score where that occurs? Negative 0.4. Come up to the top. Find my cursor. Here it is. Negative 0.42. What would that look like in an Excel world? Well, we're going to use, if once you're given a probability, that's what the 0.6628 is. You turn that into, you got to check, is that the cumulative? Nope, it's not a less than or equal to probability. Turn it into a less than or equal to probability. Put that in as the probability, comma, put the value of the mean, it's 1 in this case, put the value of the standard deviation 0, and it's going to give you exactly the same value. That's how we do points in the distribution. All right, what about non-standard normal distributions? Well, they have a mean, a value of the mean of mu, a value of the standard deviation of sigma. So now when we draw the picture, it's going to be a mound-shaped symmetric distribution. We're going to draw mu here in the middle. Now we typically think of these as the distributions of our x's. We use the symbol z for standard normals. And now we need to figure out how to work with those. Well, the beauty of the standard normal distributions is any normal distribution can be made to look like standard normals, and we can solve it using our good old friend, the z-score. We saw the z-score transformation, or the z-score, back when we were talking about outliers. It was one of our measures of relative standing. It was a method of detecting outliers, but it's also going to be the key to making standard normal distributions work to solve all other normal distributions. Very few things in life have a mean of 0 and a standard deviation of 1. It just doesn't occur very often. But there are normal distributions everywhere. And the way that we're going to solve them, one way, let's say it this way, one way of solving them, the kind of the traditional, the classic approach to solving normal probabilities, is to make them look like or behave like standard normals and then use our standard normal tables. That's why this lesson's so important, being able to find normal probabilities in the table. Or being able to find normal probabilities in Excel is so crucial. Now let me let you in on a little secret here. Let's go back. Let's see if I can go back. I'm trying to go back. Let's see. Here we go. Here we go. So these tables, when I make normals look like standard normals, I'm going to be able to use this table. And I can use it for any normal distribution. However, here's the secret. These functions, the normal distribution function we saw earlier, the normal inverse function, they allow me to put in any value of mu and sigma that I want. They work great for standard normals. but they're also going to work great for other normal distributions. If I have a distribution that has a mean of 100 and a standard deviation of 10, I can use these functions. And that, my friends, is going to make your life a lot easier. But not right now, because right now is a really good place to stop. I'm 20 minutes in. Let's take a break here. And when I come back, I'll show you how to work with non-normal or non-standard normal distributions. I think I said that right. The X's and not the Z's. I'll see you then.